This is Module 9, Address Resolution of the Cisco Academy Introduction to Network version 7.0. Comparing MAC addresses along with IP addresses. As previously discussed, Layer 2 physical addresses, or the MAC address, this is used for NIC-to-NIC communications on the same Ethernet network. If we are going to go from one network to another, we would have to use a Layer 3 logical address, or IP address. It makes no difference whether it is IPv4 or IPv6. It allows us to go from one network to another. So the logical Layer 3 addresses are used to send the packet from the source to a device to a destination. Layer 2 addresses are used to deliver frames from one NIC to another NIC on the same network. If a destination IP address is on the same network, the destination MAC address will be that of the destination device. Going from one network to another, the IP addresses will stay the same, although the Layer 2 addressing will change because the media will change. As we can see here in this diagram, when the destination IP address is on the remote network, the destination MAC address is that of the default gateway. So if PC1 was to contact PC2, PC1 would send an op request. All devices on the 192.168.10 network would see the op request. Router 1 would respond with the MAC address of the default gateway. This is referred to as proxy op, in that the router is acting as our proxy to get the packet or the frame to the next destination. ARP is used by IPv4 to associate the IPv4 address of a device with the MAC address of the device. Reverse op would get you the IP address for a device whose MAC address you already know. ICMP version 6 is used by IPv6 to associate the IPv6 address of a device with the MAC address of the device NIC. The diagram that I have built on Packet Tracer is the same one that was in the Cisco Network Academy slides. The only difference would be the MAC addresses of the different interfaces. I will use this diagram, which has been configured, to demonstrate how the MAC address will change at each hop along the way, while the IP addresses stay the same. I have gone on and collected the MAC addresses from the PCs and the routers. To collect the MAC address from a PC, you need only go into the command prompt and type in the command ipconfig /all. This command will show you the physical address, as we see here, is 0030A35334B8. To collect the MAC addresses from a router, first enter the router and get into privileged exec mode. To collect the address, the MAC address of an interface, simply put show interface gigabit 0/0, and it will tell you that the hardware is a gigabit Ethernet with a MAC address of 0003 E4 AB 3601. If I want to see the exit interface of the same router, I would simply change the interface that I want to show. And here, you'll notice the MAC address is the same, except it is 3602 as the exit. The diagram has been built exactly as it was in the PowerPoint presentation. All addressing is as was designated in the presentation. And here I have recorded the MAC addresses of the different interfaces. PC1 ends in 34B8. The entry to R1 is 3601. The entry or the exit of R1 is 3602. The entry of R2 is 1E02. The exit being 1E01. And the final PC, PC2, ends in 91D6. I will now switch over to simulation mode. In simulation mode, we can capture packets. And I'm going to go to PC1 first and tell it to ping PC2. In PC1, I merely need to say ping 10.1.1.10 to make it ping PC2. Once I tell it to ping from PC1 to PC2, I will also be running the simulation. As we can see in the simulation, the packets are going from PC to switch, from switch to router, from router to router, router to switch, and finally back to PC2. PC2 will respond to the ping request with an echo response. I'm going to stop the simulation at that point. I can now take a look at the packets that went from PC1 to R1. We can see the packet. It'll be listed as going from PC1 to switch 1 and then switch 1 to R1. Either packet will give us the same information, as the switch would not change the MAC addresses. It will simply forward the information. As we can see here, in the frame going from PC1 to R1, the first leg, the source MAC address is 34B8, that of PC1, while the destination MAC ending in 3601 is that of the ingress interface of R1 acting as the default gateway. If we were to take a look at the IP addresses, the source IP address being 192.168.10.10, that of PC1, while the destination address is 10.1.1.10. After examining the packet that went between PC1 and R1, we can now examine the packet that goes between R1 and R2, simply by selecting it here on the right. As we can see here, for the second leg going between R1 and R2, the source MAC address is 3602. This is the exit interface of R1. The destination MAC address ending in 1E02 is the ingress or gigabit 01 of R2. So we are going from a source MAC of R1 to a destination MAC of R2. The IP addresses remain the same, with a source of PC1 being 192.168.10.10 and a destination IP, that of PC2, being 10.1.1.10. We can now examine the packet through the next stage, from R2 going to PC2. I will select the R2 going to switch 2. As we can see here, the source MAC address ending in 1E01 was that of the exit interface of R2, while the destination MAC address ending in 91D6 was that of PC2. The IP addresses, the source remained the same at 192.168.10.10, while the destination IP address was again the same as it began, the address of PC2 at 10.1.1.10. We have seen that as the packet went from PC1 to PC2, the IP addresses remained the same, while the MAC address changed at each stage. We can look at the return traffic, which would have been the echo reply. I can look at the information that came from PC2 going to switch 2. As we can see here, the source MAC address, now ending in 91D6, is that of PC2, while the destination MAC address, ending in 1E01, is that of the router R2. We can see that the source IP is now 10.1.1.10, while the destination is that of PC1 being 192.168.10.10. We can now take a look at the packet going from R2 to R1. We can see here how the source MAC address, now ending in 1E02, is that of the interface of R2 that was previously the ingress. It is now an egress interface going to R1. The destination MAC address is that of R1's interface directly connected to R2, ending in 3602. As you can see here, the source IP remained the same at 10.1.1.10, while the destination IP is that of R1, or of PC1, which was 192.168.10.10. Now that the packet has gotten to R1, the final step would be going from R1 to PC1. If we take a look at the packet leaving R1 going to PC1, we can see here on the final leg going from R1 back to PC1, the MAC address of the source is that of R1 being 3601, while the destination MAC is that of PC1 being 34B8. The IP addresses have remained constant and the same throughout, with a source of 10.1.1.10 and a destination of 192.168.10.10. So throughout this exercise, we have sent an echo request from PC1 to PC2, and the echo reply returning from PC2 back to PC1. The IP addresses have stayed the same, while at each hop, the MAC address changed. You can see how in simulation mode in Packet Tracer, it is a very handy tool to take a look at how information changes from the source to the destination. ARP is an extremely important protocol when it comes to transferring data. If a host does not know the MAC address of the destination, it must request it through the ARP process. A device will use ARP to determine the destination MAC address of a local device when it knows its IPv4 address. A host may also use reverse ARP if it knows the MAC address but needs the IP. In this section, we will concentrate on only ARP, which will give us a MAC address for a known IP. It provides us two basic functions: resolving IPv4 addresses to MAC addresses and maintaining an ARP table of IPv4 to MAC address mappings. To send a frame, a device will search its ARP table first for a destination IPv4 address and a corresponding MAC address. If the packet's destination IPv4 address is on the same network, the device will search the ARP table for the destination IPv4 address. If the destination IPv4 address is on a different network, the device will search the ARP table for the IPv4 address of the default gateway. If the device locates the IPv4 address, its corresponding MAC address is used as the destination MAC address in the frame. If there is no ARP table entry found, then the device sends an ARP request. When a router responds with the MAC address of the default gateway, it is called proxy ARP, as the router is acting as our proxy to get our packet to its final destination. If there's entries in the ARP table that need to be removed, the ARP table can be cleared in either a PC or on a router or a switch. Entries in the ARP table are not permanent though, and they are removed when an ARP cache timer expires after a specific period of time. The duration of the ARP cache timer differs depending upon the operating system. ARP table entries can also be removed manually by the administrator. As we can see in the diagram, depending upon the equipment, the names and numbers of the interfaces may change. If we wish to see the ARP table on a router, we can say show IP ARP. On a computer, we can say ARP space -A. Either will give us a current listing of the table of ARP to IP addresses in either devices. ARP requests are received and processed by every device on the local network. Excessive ARP broadcasts can cause some reduction in performance. Since ARP is a broadcast, while the broadcast is going out, no other devices can be sending or receiving data. ARP replies can be spoofed by a threat actor to perform an ARP poisoning attack, such as when a host requests the MAC address of the default gateway and a threat actor sends a gratuitous ARP listing themselves as the default gateway. The unsuspecting host then sends all messages to the threat actor, who in turn forwards them out through the router, but recording all data that was sent. Enterprise-level switches includes mitigation techniques to protect against ARP attacks. We use a process called DHCP snooping that builds a table of IP addresses to MAC addresses. If a threat actor tries to insert their own MAC address, the table will recognize the change and shut off the port the threat actor is attached to. To illustrate how a switch learns MAC addresses, I have built the following diagram. The only configuration necessary was the IP address, subnet mask, and default gateway on each of the PCs. The switch received no configuration. I have entered the switch, and I'm going to take a look at the MAC address table. First, I need to be in privilege mode, so I will type in EN. Now I will say show MAC address table. And we can see that the table is empty because the computers, the hosts, have not sent any information. Otherwise, the MAC address table would be populated. I have entered simulation mode and will ask the host of 200.0.0.3 to ping host 200.0.0.2. As we can see, an op request is going to all PCs, but only 200.0.0.2 will reply to 200.0.0.3. The pings now go only to 200.0.0.2, which replies back to the request from 200.0.0.3. If we were to look at the MAC address table on the switch, which was previously empty, we will now see that we have learned two MAC addresses, that from the computer of 200.0.0.3 and that from the computer of 200.0.0.2. The 1 and 4 are still not in the MAC address table. As we have seen, until a PC either responds to a request or initiates a request, the MAC address does not appear in the MAC address table of the switch. The switch in its MAC address table will indicate which VLAN the host is a part of, the MAC address, as well as the port number and how the address was learned. This next section deals with copper cabling. IPv6 does not use ARP as IPv4 does. IPv6 uses a neighbor discovery, or ND, protocol. It is used for address resolution, router discovery, redirection services. ICMP v6 neighbor solicitation and neighbor advertisement messages are then used for device-to-device messaging, such as address resolution. ICMTP v6 router solicitation, or RS, and router advertisement messages are used for messaging between devices and routers for router discovery. ICMP v6 redirect messages are used by routers for better next hop selection. The neighbor discovery, neighbor solicitation, router solicitation, and router advertisement messages are also used to supply IPv6 addresses to host devices. A PC can send out a neighbor solicitation, or NS message, asking who has a particular address and to get the MAC address. The neighbor uses a neighbor advertisement message providing the IP address of the requester, its own IP address, and its own MAC address. So IPv6 devices use ND to resolve the MAC address of a known IPv6 address. ICMP v6 neighbor solicitation messages are sent using special Ethernet and IPv6 multicast addresses. The neighbor solicitation is also used to ensure that no other devices on the network have the same IPv6 address. This concludes Module 9.